Hello everyone, I am Dr. Anita Roy and today we are going to discuss about molecular symmetry and symmetry elements. And further we will discuss how molecular symmetry is related to group theory. If you want to know more about group theory, in my previous video it is there and you can watch it. The link is given in the description box. So before I start our today's discussion, I'm going to give a brief idea about a molecule. Molecules are finite and concrete particles in all states of aggregation consisting of defined number of atoms. Thus, symmetry is an important thing for determining the molecular structure. For a vivid idea, we need to know about symmetry element and symmetry operation. Symmetry operation is nothing but an operation which can take a certain configuration of a molecule to an equivalent configuration after the operation. So for doing any symmetry operation, we need some tool. Those are symmetry elements. Symmetry elements are identity, plane of symmetry, axis of symmetry, center of symmetry, and improper axis of symmetry. These are the procedure of operation. In identity operation, there is actually nothing is done. In plane of symmetry, reflection in the plane is observed. Axis of symmetry, rotation about the axis. Center of symmetry is inversion of all atom through a center. And improper axis of symmetry needs a rotation and then a reflection. The reflection should be perpendicular to the rotational axis. To describe this symmetry element and the symmetry operation, I am going to use some paper cutouts to make it more easy to understand. So these are the symmetry elements, and now we'll use some paper cutout to make it easy. Yes. So it's a triangle, right? Axis of symmetry tells us that on rotation around that axis, we are going to get a equivalent configuration. So axis of symmetry can be classified into two parts: primary axis of symmetry and auxiliary axis of symmetry. We have taken a molecular structure to determine the axis of symmetry. So BH3 is a molecule I have taken. BH3, the structure is nothing but a trigonal planar structure. Let's say this is a trigonal planar. So hydrogens are in the three corners of it and boron stays at the center. So axis of symmetry is operating along the center. So if I rotate the molecule in 120 degree, then I am going to get the exact configuration. That means the Cn is 2 pi by theta. That means 2 pi means 2 into 180 degree, 360 degree by 120 degree, because the rotation is 120 degree for a trigonal planar case, and we are going to get n equals to 3. That means the axis of rotation is C3. So axis of symmetry is denoted with respect to Cn, where n is the order. In this case, the order is 3. If we will rotate the axis of symmetry n times with respect to the number of fold, then we are going to get identity element. That means there is no change in the position. So if we consider this BH3 molecule, we have a C3 axis which is a principal axis. Along with that, C2 axis is also there. As we know, the number of fold for C3 is greater than C2. That's why C3 is the primary rotational axis here and C2 is the auxiliary rotational axis. The C2 axis work like this. Consider this is boron. It is connected with 3 hydrogens, and the C2 will be like this. Okay, so only the positional change of hydrogen is happening over here. So C2 is the auxiliary rotational axis and C3 is the primary rotational axis. Then plane of symmetry. Plane of symmetry, which is nothing but a reflection of plane. It is represented by sigma. Plane of symmetry can be classified into 3 parts. Those are vertical plane, horizontal plane and dihedral plane. So what is a vertical plane? Vertical plane is a plane which will consist the principal axis of rotation. So if I take the similar case of BH3 molecule, the principal axis of rotation passes through boron. Now if I put a plane like this, we are going to get similar thing, right? We are going to get just the exchange of the position of hydrogen, and this plane contains the principal axis of symmetry. That's why it is known as sigma V. If this plane is horizontal or perpendicular to the principal axis of rotation, then it will be sigma H. Here we have sigma V as well as sigma H. Sigma H is nothing but the molecular plane over here. And dihedral plane is a plane which intersects the cross section of two C2 axes. If we consider PTCl4 or like this, we can consider it's a platinum tetrachloro complex. So the 4 sides are 4 chlorine. Now in this case, what is the axis of symmetry? It is C4, right? Because 90-degree rotation is only going to give the equivalent configuration. So the order is 4 and the principal axis of symmetry is C4. Now we have C2 axis as well. So two C2 axes are like this along the platinum chlorine bond, and two C2 axes are there which is in between the chlorine bonds, like in between this. These are also C2 axes. If I rotate the molecule 180 degree with respect to this part, then we are going to get the same thing, right? So this is another kind of C2 axis present. In this case, we are going to get a sigma D. Sigma D is nothing but a plane which intersects the cross section of two C2 axes. Here this is a C2, this is a C2 axis, and the cross section of that, when this plane is going to intersect the cross section like this, this is going to be the sigma D or dihedral plane. Inversion center is a point through which all the atoms can be inverted, or we are going to get just the inversion part through the point, right? So if I consider this molecule where hydrogen is here, and just after passing through the inversion center, it is going in the opposite phase. We are going to get the same atom after passing through the center. So this center is known as inversion center. Another one is improper axis of symmetry, which is denoted by SN. So it is related to two operations. One is rotation, which is followed by a reflection. So let's take this molecule. Now if I am taking this one, so after rotation, what is happening? This one part will go just after rotation, it will be here. Okay, but this is not the actual case, because these are not equivalent after rotation. So we need to get a reflection, and the reflection will be perpendicular to the rotational axis, and we are going to get a reflection which is equivalent to this molecule. That means this molecule is having improper axis of symmetry. Then side symmetry. Side symmetry is symmetry with respect to a particular site. So whenever we are discussing all those symmetry element with a molecule, the overall molecular structure is considered here. So in case of side symmetry, only a particular point of the structure is considered. So until the discussion, we have understood that all molecules have certain symmetry elements required for certain operations. Those complete set of symmetry elements will form a group which is known as point group. Now we are going to discuss here about point group and how the groups are getting their nomenclature. With respect to Schoenflies notation, we are going to get the name of the group. So for doing the nomenclature of the point group, I have chosen a molecule, a model of a molecule to describe this. So I have built one ammonia molecule. So we all know that ammonia is pyramidal in nature, trigonal pyramidal. So here it is nitrogen. These are 3 hydrogens. Now, what is the proper axis of symmetry in a pyramidal molecule? Whenever we are going to do the Schoenflies nomenclature for a particular point group, first thing we need to choose the axis of rotation. Okay, so depending on the axis of rotation, the name can be different. So C we are going to use for proper axis, S for improper axis, D for proper axis perpendicular to NC2 axis. Another sets are also there. For highly symmetric element, we have 3 different options. Those are T for tetrahedral, O for octahedral, I denotes for icosahedral. In case of ammonia molecule, the rotation regarding the proper axis of symmetry is 120 degree, and thus the proper axis of symmetry for the ammonia molecule is C3 for this one. It's a 120 degree rotation and it is going to be in the same place, same equivalent configuration. So what we are going to write? First, proper axis we have chosen, that is C, and what is the order? It is 3, C3. Then we have to go for the next part, that is the subscript, which is the highest order. The highest order I have already written, that is 3. We have only one thing, that is one kind of rotation is there, so it is 3. And next one is we have to check the presence of any plane of symmetry are there or not. So we can consider this as a plane of symmetry. Now where it is possible, along the bonds, along the NH bond, this is possible. Along 3 NH bond, it is going to have 3 plane of symmetry. What kind of plane of symmetry it is? We already know that plane of symmetry has 3 different notations. Those are sigma V, sigma H and sigma D. For this particular case, it is a sigma which contains the principal axis. That's why it is sigma V. So next thing what we have to do, we have to write the nature of the plane of symmetry, which is sigma V. So we are writing V in the subscript. So finally we are going to get the nomenclature of a ammonia molecule. So ammonia molecule belongs to C3V point group according to Schoenflies notation. So other than this, if a molecule which has only center of inversion, and E or identity. Identity is common for every molecule. So that point group have I in subscript. So it will be denoted as Ci if only inversion center is present. In case of a molecule, if it has only plane of symmetry, no other elements other than identity, which already I have told, which is common for every molecular point group, then it will be denoted as Cs. For linear molecule, it can be C infinity V or D infinity H. So these point groups are broadly classified into three parts. Those are molecules of low symmetry, MLS, molecules of high symmetry, MHS, and molecules of spatial symmetry, MSS. These three parts which I have discussed, that MLS, MHS and MSS, this three category is defined in this chart. So molecules with low symmetry has non-axial, it is categorized as non-axial, then axial, then dihedral, linear and cubic. These are the symbols used. Generator means what are the symmetry elements present in the system, that is known as generator, and what will be the corresponding order. Till now we have already understood that order is the number of symmetry elements present in the particular point group. So in case of the first one, I have chosen C1. That means C1 there is no other operation except identity operation. So only one symmetry element is present in this group. That's why the order is 1. And the symmetry element is E or identity. For any chiral kind of compound, we are going to get C1 as point group. Like that, we have discussed different point group and we already know how to determine the point group with respect to a particular molecule from our last discussion. In the next part, we are going to discuss how this point group is related to the group theory, which I have already discussed in the previous video. So we already have an idea about group multiplication table, which I have discussed in the previous video. The link is given in the description box. You can always watch that for better understanding. So with the same molecule, ammonia, which we have determined the point group is C3V, we are going to discuss how the multiplication table is related, how we can form a group multiplication table for a ammonia molecule. Now, ammonia molecule, the point group is C3V. We have to write here in the intersection point the C3V, the name of the point group. Then we have to write the elements of symmetry. So we will discuss the group multiplication table with respect to ammonia molecule. The point group we have already derived, that is C3V. So we have to write the name of the point group in the intersection of this first row and this column. Okay. So as we know C3V, so order is 3 into 2, that is 6. Order is 6 in C3V, that means it should have 6 symmetry elements. Those are E, identity, C3, that is the principal axis of rotation, then C32. C32 is nothing but the operation of C3 is carried out twice. C3, and why we have not mentioned C3 cube? Because we already know that C3 cube is nothing but E from a theory. And 3 more sigma planes are there. So I have denoted it with respect to this 3 hydrogen. Consider this is A, B and C. So the sigma plane is like with respect to A, B and C. So total 6 symmetry elements are present. So according to group multiplication table, as it is a Latin square, so no symmetry element should be repeated in any row or any column, which is verified in this group multiplication table or GMT. We'll discuss this with respect to the operations. So for formation of a GMT, we multiply E into E. When E is multiplied with anything, it will be unchanged, which is according to group theory, one of the theory. Identity law. According to identity law, when identity element is commuted with any other element, those elements will remain unchanged. So it is happening here. Then the same thing, E is commuted with all those elements remaining unchanged with respect to the operation. Then C3 into C3. That means C3 into E, which is E. C3 into C3, that means first operation is C3 followed by second operation, which is also another C3. So better I give 3 positions for this 3 hydrogen and I'm going to rotate it. So C3, first C3 I'm doing. It will be like this. Okay. And then again one more C3. It will be like this. So after the operation, we are going to get that C3 into C3 is nothing but C3 2. Because if I do the operation twice, we are going to get this one. Then C3 into C3 2, which is nothing but C3 3, which is a identity. Then I think it will be easy to understand from the helicopter view. So I have drawn the molecule, the ammonia molecule from the helicopter view, which is nothing but this one, the planar version, and N is the center. So now I am doing an operation and we are going to see how it is related with the group multiplication table. Let's say C3 into sigma C. C3 into sigma C. So what value we are going to get? Sigma B. We'll just check whether we are going to get the same or not. So C3 I am operating. This is the primary position, H1, H2, H3, A plane, B plane and C plane I am considering. Now C3 means one rotation, 120 degree. We are going to get this one. And after that, sigma C. Sigma C is nothing but a plane of symmetry with respect to C, this plane, this C plane. Hydrogen, which is denoted as C, this plane. And we are going to get just the interconversion of position of HA1 and H2B. We are going to get this position. So same thing, here it is sigma B. So if I operate, this is the original one, and if I operate sigma B with respect to the original one, which is nothing but this one, we are going to get the interchange of the position of C and A, which is this one. So operation of C3 into sigma C is going to denote sigma B, which is represented in the group multiplication table. So these are some examples, and if you just do the operation with respect to ammonia molecule, you are going to get the whole idea of a group multiplication table. So same thing you have to do the operation and you are going to check whether it is similar with respect to the operation mentioned in the GMT or not. So it can be your task. So next thing you need to know that C3 is an axis of rotation, C32 is also another axis of rotation. How these two are related? These two are conjugate with each other. Okay, so as if these two elements are conjugate with each other, according to group theory, they are a particular class. Same thing, sigma A, B and C, these three are three sigma planes, but they are forming a class because they are conjugate with respect to each other. So in this group multiplication table for C3V, we have 6 symmetry elements which is similar to the order of the group, and this 6 symmetry element is denoted into 3 classes. One is identity, another one is this axis of symmetry class, another one is plane of symmetry class. Okay, this is the matrix representation of symmetry element. So for doing any matrix representation, first of all we have to choose a point and 3 coordination sites, right? So x, y, z coordination sites, and one point I have denoted, that is this point. Let's say point P at x, y, z coordination. Now we have already encountered with 5 symmetry operations. Those are E, sigma. E is nothing but identity, sigma plane of symmetry, I center of inversion, Cn proper axis of symmetry, and Sn improper axis of symmetry. Now we are going to change, or we are going to transform our symmetry element into the corresponding matrix representation. So identity, upon identity operation, we have known that there is actually no change in position, right? If there is no change in position, that means x, y, z will remain same. There is no change with respect to identity or E operation. To get the same value, we need a unit matrix. So this is 1 0 0 0 1 0 and 0 0 1 is going to give same set of coordination site. Okay, this is the matrix representation of identity element. So next one is reflection or plane of symmetry. So reflection point of x, y, z we are going to determine with respect to 3 plane of symmetry, which is xy, sigma xy, sigma yz and sigma xz. Sigma xy, when we are operating sigma xy with respect to point P, which the coordinate is xyz, only the z coordinate is going to change because it's a mirror reflection. So we are going to get xy but minus z, right? Minus z is represented by z bar. So to get the same thing, we need this matrix 1 0 0 0 1 0 0 0 minus 1, because only the z coordinate, z point is inversed with respect to xy. So for the other 2 cases as well, the plane what we are considering, rest of that plane, other point is going to inverse. So in case of yz, we are going to get inverse of x point. So we are going to get minus x or x bar yz. So getting a x bar, we need minus 1. So minus 1 0 0 0 1 0 0 0 1. So I think you can do now the another part, which is xz, which is nothing but the inverse of the y coordinate. It's the same thing we are going to get. In center of inversion is nothing but the complete inversion of all three coordinates. That means x, y, z coordinate is going to change into minus x, minus y, minus z. So it is represented by a inversion matrix, that is minus 1, 0, 0. And when it is operating with x, it is going to be minus x or x bar, y bar, z bar. To get this, we need this operation. Then is proper rotation or axis of proper rotation. So for rotation, when we are rotating a point, then it is related with the angle of rotation. Here it is the point. Let's say the coordinate is xy. So when we are doing any proper rotation, we have to consider z-axis as axis of rotation. So when we are considering z as axis of rotation and we are rotating theta angle, we are going to get 2 points. First of all, the first position is this one, x1, y1, and we are going to change this position with respect to theta, and that is x2, y2. So now the new position x2 is equals to, this is trigonometric formula, x2 equals to x1 cos theta minus y1 sin theta, and y2 is x1 sin theta plus y1 cos theta. So when we are representing proper axis of rotation, actually as if the rotation is done with respect to z operator, so z remain unchanged, only the position of x1 and y1 is changed to x2 and y2. So from this equation we are going to get what are the product, the elements from the product we write here, which are the which will form the matrix, that is cos theta minus sin theta, 0, sin theta, cos theta minus sin theta, and 0, then sin theta plus cos theta, 0. So for clockwise rotation, here we have done with respect to anti-clockwise, and always any kind of rotation when we are doing, it should be with respect to clockwise rotation we are doing. So here as if we have done it in anti-clockwise manner, so we have to convert the anti-clockwise matrix to clockwise, which is nothing but the change in sign. So cos theta minus cos theta is nothing but cos theta, right? If I change the theta with respect to minus theta, we know that cos minus theta is nothing but cos theta. Sin minus theta is minus sin theta, which becomes sin theta, and so on. So I have changed this one. So this is the matrix representation of proper rotation. Now with this thing, I need, as if angle of rotation is needed to determine the particular mathematical value, I have this table, sin 0, sin theta. Here the theta values or the angle of rotations are there, and corresponding sin theta and cos theta values are given here. And with respect to a particular angle of rotation, we will change the matrix sign with respect to this values. Let's say C1 is nothing but the rotation is carried out in 360 degree, a complete rotation. So sin theta value is 0, cos theta value is 1. If I put the sin theta and cos theta value, we are going to get actually the unit matrix, which is nothing but similar with the identity operation. Okay, then C2 means cos theta, the angle of rotation is 180 degree for C2, and if I get the values of sin 180 degree, cos 180 degree, the values are 0 and minus 1. So just replace the position with respect to the values. We are going to get this operation, this matrix. So the matrix representation of C2 is like this, and so on we can do with respect to the particular operation, particular angle of theta. We are going to get a particular set of proper axis of symmetry. So improper axis of rotation or improper rotation, which is denoted by Sn, we have already understood that improper axis of rotation is carried out by two following operation. Those are proper axis of rotation followed by a plane of symmetry, and the plane should be perpendicular to the proper axis. Right now we have discussed that proper axis means the axis should be along z-axis, so we have denoted CNZ, and if the plane is perpendicular to z-axis, the plane must be sigma xy. So sigma Sn is nothing but the rotation operation into sigma xy. Sigma xy we have already discussed in this one. Sigma xy matrix, just multiply this two. We are going to get the matrix representation of improper axis of rotation. So in our next discussion, we are going to discuss regarding character table, great orthogonality theorem, and what are the applications of group theory, how all this thing, how all the derivations, how all the matrix representations are related with respect to group theory. We are going to get that thing in the next class. Till then, bye.